Hi, I'm Katarina, and for those of you who have gone camping before, you might know about this cool thing that you can throw in your fire for some cool looking flames. When I pour this in, the orange flames will turn blue.
What did he say?
Wild, right? So, what just happened here? Basically, we took an ionic compound, added energy, in the form of heat, to get these colorful flames. But what makes these flames colorful? Well, light is a form of electromagnetic radiation, just with varying wavelengths and frequencies. So for now, let's focus on the wavelength. A wavelength is the distance between two peaks or troughs and can vary greatly in size. This variation in wavelength is shown on the electromagnetic spectrum, ranging from gamma to AM waves. The wavelengths increase in size as you move across. In the center of all this is visible light. It goes in the opposite of Roy G. Biv and ranges from violet at approximately 400 nanometers to red with approximately 700 nanometers. So let's take a look at the math behind all this. Wavelength times frequency equals the speed of light, which is a constant. This means that a wavelength is inversely proportional to the frequency of a wave. Frequency is the number of waves that pass through a given point in a unit of time. Like I mentioned, the speed of light is a constant, and it equals 2.998 times 10 to the 8th meters per second. Another important equation to know is the energy of a photon, which equals Planck's constant times frequency. Wavelength does not equal Planck's constant, even if they look a bit similar. Planck's constant equals 6.626 times 10 to the negative 34 joule seconds. So let's dive deeper. When electrons absorb energy, they're in an excited state and will jump to a higher energy level. Excited electrons are unstable and will eventually return to its lowest energy level. In doing so, it will emit a photon. This process is known as electron transition. A photon represents a quantum of electromagnetic radiation and can show the energy difference between each initial and final energy level, which is seen on the line emission spectrum. With a spectrometer, each of these photons are characterized by a line. These lines make an emission spectrum, which is unique to each element, just like a human's fingerprints. So, can we see these emissions? Well, yes and no. With the naked eye, we can see one combination of all emission lines present, but not each line separately like with a spectrometer. Think of this like food dye. Red and blue are mixed together to get purple. The primary colors are like emission lines, while purple is the result of each line together. So let's try this in the lab with a few different solutions. I dissolved each of these salts in water and mixed in ethanol to provide something for the fire to ignite. You can also see me almost set my school on fire. With that crisis averted, you can really appreciate how such beautiful colors can come from metals. So, when you have your next campfire, socially distanced of course, I hope that you can show off your new knowledge. Stay safe, everyone!